Let us prove that there are infinitely many primes. We assume to the contrary that there are finitely many primes, namely P1, P2, P3, pk. So we assume, suppose if possible, that there are only this many number of primes, and then we take or let n equal to p1 times p2 times p3 times pk plus 1. Now n is not divisible by p1 because n leaves the remainder 1 when divided by p1. N is not divisible by p2. N is not divisible by any of those prime. But by fundamental theorem of arithmetic, there exists a prime p such that p divide n. This is true for every natural number n that is greater than 1. Of course, n has to be greater than 1. There is at least one prime p. Of course, p1 may be taken to be 2, so 2 plus 1, at least n has to be greater than 3. So there exists a prime p such that p divide n. Now that prime cannot be equal to p1 because p1 does not divide n. That prime cannot be equal to p2 because p2 does not divide n. Then p is not equal to p1, p is not equal to p2, p is not equal to pk. And so we found a new prime. And so we found a new prime. We found a new prime different from each of pi. So that's a contradiction because we are assuming that there are finitely many primes, namely p1, p2, pk are the only primes, and we found another prime. So why did we get such a contradiction? That is a contradiction because we are assuming finitely many primes. Of course, this is a contradiction to our assumption that there are finitely many primes, so we conclude that there are infinitely many primes.